Okay, so this is a course about how the right light improves our lives. We're going to go through a number of topics. We're going to cover and answer questions, fun questions such as how can the mobile phone show you which offices can cause more headaches, why astronomers and criminals hate the color blue, why a city like Athens from above looks yellow, but in the coming years this could change and the city could look blue. What colors, what color light can mess our biological rhythms and sleep, and are people working night shifts in greater risk of cancer? Questions like that and more we're going to be covered in this course. I guess the main sections of this course will be, we're going to start off with some definitions of light and lighting. Then we're going to look at the light source technologies. What are the main technologies that all the families of products are based on? We're going to look at the principles of operation of each different type of lamp. And then we're going to start looking at how the light and the light sources influence our health. So we're going to look at several health issues, and hopefully we'll be able to make matches between lamp technologies and everyday needs and applications. The things we're going to be talking about are basically related to the book The Right Light. It's by me, Spiros Kitsinellis. It's published by CRC, Taylor and Francis. You can go to Amazon and order it, or you could go at the CRC page. And the third option, of course, is to go to my personal website and inquire, www.thenightlab.com. Or at the end of the day, you can send me an email, kitsinellis@yahoo.gr, for questions about the book, but basically about any possible question you want to ask about the course. I'm a doctor of physical chemistry and spectroscopy. I have been a researcher of light sources in various universities around the world. My most recent position was at Ehime University in Japan. I have worked at Sheffield University in England, Toulouse, Paul Sabatier University in Toulouse in France, National Technical University of Athens in Greece, at the central laboratories of Philips Lighting in Eindhoven. So I have extensive experience about the subject of light sources and lighting technologies. And in parallel, I'm also spending time doing science communication through seminars like this, and also books and articles and other projects. We all know that there's some kind of magic in converting matter to immaterial light, and we can see that pretty much every religious or spiritual process in our history and in our world is related in some way to light and a flame. In ancient Greece we had the flame for the Olympic Games. We have candles in pretty much every religion. Light is related to our spiritual world a lot. In fact, I think it's the Bible that mentions God only by using the word light. So in the human subconscious, light is related to the magic of existence and something divine. Divinity that one can find also in art. With the right light, you can turn and transform even boring constructions into something beautiful and pleasing to the eye. In this slide I'm showing an old gas factory in Greece, the biggest cable bridge in Rio, and of course the Parthenon and the Acropolis. The blue sources and the red sources illuminating these structures definitely make it look much better. Light sources, artificial light sources, man-made, light sources are also an index of economic development and human presence. If you look at Earth from space, the only visible human product is basically the illumination sources, and by looking at the map of these night lights, one can see where people have developed stronger economies and of course a more active presence. Now let's not forget that 20% of the world's electric energy is consumed by light sources, and there's about 13 billion incandescent lamps and another 8 billion lamps of other types. The point I'm trying to make here is that whenever we talk about light sources, in reality we are talking about huge numbers when it comes to the world economy and the world's environment. So even slight improvements in the efficacy of a lamp can have a huge impact on the environment and on the economy. So what is light? Basically, when we talk about the visible light, it's a small window in the electromagnetic spectrum. On the high energy end, you start with cosmic rays, and then X-rays, and then ultraviolet. Then you find this small window we call visible light. It starts from the violet, and it extends at 400 nanometers, and it extends to red at 700 nanometers. And after red, on the lower energy side, one finds the infrared radiation, and then the microwaves and the radio waves. So it's a small window in the electromagnetic spectrum that our eyes are tuned in. Historically, there's been, one can say, philosophical and scientific debate about what light is. There was basically two sides, with one of them insisting that light is waves, basically waves, and there was another side believing that light was particles. For example, Newton thought, because of the reflection property of light, that we are dealing with particles. On the other side, used the refraction as his argument for promoting the wave nature. De Broglie, the Nobel Prize winner, also showed the wave-particle duality with his famous equation lambda equals h over p, the momentum. So there was historically a long debate, but in the end, 20th century scientists put this debate to an end by showing that we're dealing with both this dual nature of light. So you have rainbows, which is the result of refraction, and you have red sunsets, again because red is refracted less than blue. So one property of light, which is refraction, it's light splitting into its constituent colors when it goes through another medium such as a prism. Here what we need to point is that shorter wavelengths are refracted to higher degrees than longer ones, and this is the reason why at sunset you have this reddish, orange reddish sky. The other property of light is scattering, and when it comes to scattering, shorter wavelengths like violet and blue will scatter more than the longer wavelengths. You have different types of scattering, like Rayleigh scattering and Mealy scattering, and this is why the sky is blue. The sky is blue because of blue being scattered much more than the other colors, and the sunset is red because of refraction. So you have two different things here, and we need to point these out. If any of you have seen the film or have read the book Day of the Triffids, then you realize how important our ability to see light is. If, according to the book, if you see the book, you realize that, you know, if you lose vision, if humanity lost vision tomorrow, civilization would collapse almost immediately, and probably the human race will be extinct. I'm making this point here in order to emphasize the importance of vision and light sources for our very existence. So what about myopia or farsightedness? Well, this is caused when light is focused on the wrong spot of the eye, and it could focus on the wrong spot either because the lens doesn't have the ability to do so, or because the size of the eye is causing this. Although the sensors on our eye, there are basically two categories of sensors. You have the cones and you have the rods. The cones are mostly responsible for color detection, and they're mainly focused in the center of the eye, the center of the retina, while the rod density is higher on the periphery of the eye, and is mostly sensitive to the sensitivity, not so much on the colors but on the brightness of the light. Although there is some sensitivity of the rods on the blue end of the spectrum, and this makes sense because if the rods are activated and play the important role during the night, then during the night the main light source from an evolution point was the moon, and the moon usually gives a cold bluish light. So it makes sense why the human eye evolved to be more sensitive to blue eye when the rods are playing the big part. So what about the cones? The cones themselves are separated into three basically groups. One group mostly sensitive to blue, the other mostly sensitive to green, and the third one mostly sensitive to red. And it's the excitement of these three groups that in the end give you the effect of white light. So basically you could simulate white light by having a light source, a red light source, or red photons, blue photons and green photons. So blue, green and red are the primary colors, and when these three combine, the human eye detects this as white color. Like we said before, the rods and the peripheral vision, they're responsible for, because they are mostly situated on the periphery of the eye, of the retina, they're more sensitive to blue light. So when you look at the cones and the three different sensitivity curves, when you put them together into one collective sensitivity curve, what you get here is the blue curve, the photopic curve, which maxes out, shows the maximum sensitivity at 555 nanometers. That's a color, yellow-green color, and this is the reason why several construction workers' vests are colored yellow-green. It's because the human eye is sensitive, is at its highest sensitivity at this nanometer, at these nanometers. And then when you look at the scotopic curve, which is the sensitivity to the eye during darkness or low illumination situations where the rods are playing a more important role, then this sensitivity curve is shifted towards the blue side of the spectrum, and in particular the maximum point moves from 555 nanometers to 507. So that's something again to remember, that you have three types of cones. The overall color sensitivity of the human eye in photopic conditions is the yellow-green, but at night, where mostly rods play the role, this curve is shifted towards the blue. So blue light would be more important to the eye at low light level conditions. Now we have what we call the circadian rhythm. The circadian rhythm is like a biological clock, is something that regulates our 24-hour day. Again, from an evolution point, the human eye would look at the sky to see if it's still daytime or if it's dark and time to go to bed. So we have evolved to be mostly sensitive to blue light. In fact, it was in recent years we discovered an extra set of sensors in the human eye, not responsible for vision, but responsible for transferring to the right parts of the brain information about what time of day it is, and how to regulate our biological clock. This sensitivity is mostly between 460 to 480 nanometers. It is at this range that light can suppress melatonin, increasingly with increased light intensity and length of exposure, of course. Light containing wavelengths greater than 530, meaning greater than the green region, does not suppress melatonin. It's mostly green, but it's green, but mostly blue light that can suppress our melatonin levels and can affect our biological clock, because our biological clocks are regulated by melatonin. The melatonin levels increase as we approach midnight, and this is supposed to put us in bed. Now, if there was blue light in the sky, the human eyes will get this information and of course not release the melatonin in the bloodstream and still keep us active. So in a sense, a blue light source can stimulate the blue sky and tell our bodies if it's time or not to go to bed. A color temperature is the temperature of a source in Kelvin at which a black body has the same color. So usually we talk about warm white sources if the color temperature is less than 3,500 Kelvin. It's a cool white source if it's more than 5,000 Kelvin, and anything between like 3,500 to 5,000 Kelvin, we call it just neutral white sources. Now the balance between the blue components of a light source and the red components of a light source is what determines if the source will be warm or cool. A lot more red will probably make the source warmer. More blue light will make the source cooler. The color rendering index is an index which determines how well the colors are rendered, as it says. And the standard is, we have a scale from 0 to 100, 100 being assigned to incandescent sources, because incandescent sources cover the entire visible spectrum. So the larger the area, the larger the portion of the visible spectrum covered by a source, the higher the color rendering index will be. And usually we deal with either line spectra or a continuous spectrum. So a continuous spectrum will have a better color rendering index. A line spectrum we have a lower one. Now let's see the different lamp technologies in a little bit more detail. The first type of light source technology is the incandescent lamp, which is basically electric current flowing through a coil, a filament, and reaching the right temperature until it starts to glow. And of course, if it starts to glow red, before extra energy will move the emissions to the rest of the visible spectrum. So here we're dealing with continuous spectrum. Incandescent sources have a continuous spectrum with mostly red light, of course, emitting, hence they are warm sources. They have a high color rendering index exactly because it's a continuous spectrum covering all the entire visible spectrum, so all colors can be reproduced. It's warm white, as we said, because it's mostly red light emitting. It is unfortunately of low efficacy because mostly the energy is converted to heat and infrared emissions, and the lifetime is quite short. We're talking about 2,000 to 2,500 hours for a simple incandescent source, possibly to a 5,000 hour lamp when we deal with a halogen incandescent source. Then we have the second type of light source technology is electric discharges or plasma sources. Here we deal with gas or vapor, which is ionized. Electrons flying through the gas or the vapor collide with the atoms of the molecules, and these collisions result in the emission of energy, and each atom or molecule has its own spectral signature. So when you're dealing with a neon gas, it's mostly red light emitted in the visible spectrum. When you're dealing with sodium, you have the very characteristic yellow lines. When you're dealing with mercury vapor, you have mostly UV lines converted with right powder, phosphorescent powder, fluorescent powder, to visible emissions. A fluorescent lamp is basically belongs to this third category. It's a mercury vapor electric discharge lamp. So you have the mercury vapor, you have a mercury drop or some milligrams of mercury and a buffer gas to help with the ignition of the lamp. Then the mercury is vaporized, then as it is in the vapor state, it collides, the atoms collide with electrons. Mostly ultraviolet radiation is emitted, specifically at 254 nanometers, and then you use the powder on the walls of the lamp to convert this ultraviolet into visible light. And of course, depending on the powder that you use, you can manipulate the final result of the light source emissions. Some more spectra with lamps. You have, like we said, a neon lamp used extensively before the coming of the LEDs. It was used extensively in signage. A neon lamp, if you look at the spectrum of a neon lamp, you have a lot of emission, atomic emission lines in the red region. Then you have the yellow, the characteristic yellow sodium lamp. The low pressure one has a very characteristic also line spectrum with a double yellow line, double line in the yellow region. Then you have the mercury fluorescent lamp, which is basically mercury ultraviolet converted by the powder to a number of visible lines, as you see. Then you have metal halides. These are high pressure lamps that contain sometimes both a mercury but also other metals in the metal halide form. The reason we use metal halide forms is to make it easier for them to vaporize. And the spectrum here, because of the high pressure, is more continuous. It covers the visible spectrum better. And finally, the third technology that is beginning to take over more and more applications these days as the lamps become better and cheaper is an LED. An LED has a more narrow emission, both in direction of light, but also narrow in the spectrum sense. It's not entirely monochromatic as a laser, but it's pretty narrow light. So usually you would get, like the spectrum shows, very narrow blue light, blue LED, and then you would combine that with a narrow green and a narrow red LED to combine them and make white light. And they come in different sizes and shapes, and these days more and more applications use them. The simplest way of making a white LED, like we said already, that one way is to combine different color LEDs in order to produce the final white result. But usually when one wants to use a single LED to produce white light, the most traditional or the most usual way is to use a blue LED that is covered by a powder, and that powder, fluorescent powder, converts some of that blue light into yellow light. It's not dissimilar to the way the fluorescent lamp works. You know, in the fluorescent lamp works, you have ultraviolet light and you convert some of that light into visible. Well, same way here, you're using specifically designed phosphors to convert a blue or sometimes even a UV LED into some more visible light to cover more regions of the visible spectrum. So a blue LED with a yellow phosphor is the cheapest, easiest way to produce white LEDs for a very large number of applications. In fact, it was the blue LED we were missing before LEDs took over all these applications. Before that, we had the amber LED, we had a green LED, and we had a red LED, but it was the blue LED missing before we can talk about white light and a true penetration into the market. And this is why this year's Nobel Prize in Physics was awarded to researchers that developed that blue LED, such as Shuji Nakamura. So white light can be created by using a blue or a UV LED and phosphor to convert some of the blue emissions into yellow, or the UV emissions into the primary colors, just like one would do with a fluorescent lamp. Again, when we first had yellow and red and green LEDs, the most usual application would be traffic lights, but now one can make white light with LEDs and the applications are basically limitless. So you can have different white light tones. Like we said before, you have warm sources and cold sources, or cool sources. And this photo here shows, the lamps on the left of each picture emit this very warm yellowish light, while the lamps on the right side of the pictures are more bright white, which is basically a cooler white. And this distinction is related to the color temperature. So the table shows the different light sources and some representative values of color temperature and CRI, color rendering index. For example, a sodium high pressure has 2000 degrees, 2100 degrees, and a medium CRI beginning from 25 reaching 85. A warm white fluorescent is 3,500 or less, with color rendering index 55 to 99. It can reach a very good value. Then you have a cool white fluorescent, higher CCT, but same range of CRIs. The metal halide is also a cool white source with medium to good CRIs. And then you have the incandescent lamp, which is a warm source, but with the perfect color rendering index. And you can see on the scale on the bottom of the picture, again, the CRI for different types of lamps. So low color temperature warm light sources are the halogen lamps, fluorescent lamps that are warm white fluorescent lamps, warm white LEDs, and of course sodium lamps, which is basically yellow. And then cool light sources, meaning high color temperature light sources, are the cool white fluorescent lamps, all types, the cool white LEDs, metal halides, and xenon lamps. And it's again obvious from the pictures that the bluish lamps are the cool white ones, and the yellowish lamps are the warm white light sources. So let's put together like a summary of the important points made based on these principles. So you have a foveal and central vision using cones, more sensitive to green and yellow light. The photopic eye sensitivity curve peaks at 555 nanometers. Then you have, as a second point, the blue light enhances the scotopic and the peripheral vision because roads are more sensitive to shorter wavelengths. And this scotopic eye sensitivity curve peaks at 507 nanometers. The light of shorter wavelengths, meaning the blue light, undergoes more particle scattering. The light of shorter wavelengths, again blue light, undergoes greater refraction. Point number 5 is that a continuous spectrum light source has a higher color rendering index than a non-continuous or near monochromatic sources. Point number 6, a non-continuous spectrum light source has a lower rendering index but usually higher efficacies than same power continuous sources. Point number 7 is that warm white light creates a cozy and relaxed atmosphere. And the final point is the opposite, which is that cool white light, more blue, stimulates us and enhances focus and alertness because it suppresses the production of melatonin, as we mentioned when we looked at the circadian rhythm slide. So now we're going to move to more specific examples of matching light source technologies with specific applications. Something very important in the field of lighting is what we call the dynamic lighting, the ability of a system to adjust to the different tasks or the different moods or the different times of day, and not just have a static light. I mean, static light means basically you buy a lamp with specific characteristics and that's it, you're stuck with those characteristics. How about if you could change during the day the lighting of your room depending the task that you're doing or your mood or the application, and that's what we call dynamic lighting. And dynamic lighting is based on these two principles that we mentioned, that a cool white light creates a stimulating and active environment, that is light sources with a color temperature more than 5000 Kelvin, and a warm white light creates a relaxing and pleasurable environment, less than 3500 degrees. A few examples would be, you have work environments when you can have meetings and focused work, or relaxation or product promotion, and again the light source and the illumination should change depending on which of these environments you want to have. Then you have changes during the working day. You have a morning, a midday, an afternoon, an evening. Daylight is changing over the course of a day, and this could be simulated by dynamic lighting. And then you have other applications where dynamic lighting could be useful, such as hospitals and nursing homes, people working at night shifts, long haul flights, and of course shops that change their products from time to time. Sleep is an important part of our lives. Like I said, the circadian rhythm is defined and controlled by our natural melatonin cycle. So if you don't want to have sleep disturbances, it's better to avoid blue light and green light, but mostly blue light with wavelengths less than 530 nanometers. And the use of a warm white light, let's say a red light at night, is more appropriate if we want to avoid these circadian disturbances. This is also why latest research is suggesting that we avoid using tablets or televisions or laptop monitors, because they emit a lot of blue light and they can also disturb our sleep by altering the melatonin cycle when used for a couple of hours before going to bed. So the suggested light sources that will not affect our natural sleep would be probably halogen lamps, warm white fluorescent lamps, warm white LEDs, and of course sodium. Of course, the ability to control the circadian rhythm by the use of cool sources, sources that emit a lot of blue, could also be beneficial if you want to actually treat people with specific disorders. An example is a delayed sleep phase syndrome, seasonal affective disorders, Alzheimer's disease, which causes sleep disturbances, jet lags, and of course night shifts. In these cases, we want to control the melatonin production, we want to control our circadian rhythms, so the use of blue light and the use of cool white sources is something that we want. Then you have the question of color rendering and how much of it, what index we want for different applications. Now, when you deal with environments where color is really important, like gallery, printing facilities, dentistry, aesthetics, restaurants, the fabric industry, museums, then you want a high rendering index, as high as possible. So we need to make sure that the light sources that we use have a color rendering index higher than 90. Halogen lamps, high CRI fluorescent and high CRI LEDs can satisfy these conditions. Then you have the situations where you're dealing with schools or offices or light industry. In those cases, a very high color rendering index is not so necessary. So any lamp with a CRI between 60 and 90 will do. Heavy industry, corridors, stairs between 40 and 60 will do. And for less than 40, such as the outdoors, for the outdoors, less than 40 would do, such as the sodium lamps that we use that have basically a very low, the lowest possible CRI, but we're using it outdoors because outdoors we're not so interested in reproducing the color as we are in having high illumination levels for us to move around. Then there is the issue of lighting and security. I'm gonna go through the sentences that I have put on this slide because they summarize everything that I need to say. So for the off-axis visual detection, which is very important in safety issues because criminals and obstacles or pedestrians come from the sides, we need light sources that stimulate the peripheral vision, light sources that basically stimulate the roads. In that case, we need lamps with blue emissions. A high color rendering index to enhance color contrast is also good. It enhances the perception of brightness and gives us accurate information on events, better recognition and surveillance. Finally, we have to choose economic systems that have a high flux, long lifetime and high efficiencies. Taking these 3 points into account, we can conclude that a cool white metal halide lamp will do the job. Cool white fluorescent lamp, specifically the inductive fluorescent lamps that have longer lifetimes, will also do. And finally, LED systems, because they have long lifetimes and color temperature that can be selected. And an extra advantage of the LED systems is that when you're dealing with the outside temperatures and weather, they can be more enduring. Here we see Athens from the sky. We see some parts of it are appear green. It's basically because of the Mercury lamps that emit some green light, some green Mercury atomic lines, and most of it is yellow because of the use of sodium lamps for outdoor lighting. Now in the future, if people start using blue light sources to enhance peripheral vision, we might see Athens turn into blue. It won't be Athens, one of the first cities to do that, but definitely cities that take lighting into very seriously and into account when designing safety will start changing from yellow, sodium yellow, to probably blue. Now sodium lamps, although they have a low color rendering index, are still valuable for certain applications. For example, when you have open roads or tunnels, when there are no pedestrians or significant traffic or known obstacles causing safety concerns, then sodium lamps are still okay to use. In places where you have a lot of fog and dust, sodium lamps are again better to use because they have higher penetration due to the longer wavelengths of yellow light compared to blue. In heavy industry and warehouses, again, there's no safety or security issue or no dangerous work being undertaken. Again, the color rendering index is not a problem here, so sodium lights can be used. Near astronomical institutions, again, they will be selected because they're longer than blue wavelengths, scattering the atmosphere less, causing less light pollution. And finally, in airports and other facilities where high fluxes and good visibility is required, but color rendering is not of importance. So these are applications where the sodium lamps, which by the way happen to be the lamps with the highest efficacy in the history of artificial light source development. So in all these applications, the sodium lamps will still be needed and used. Then we have the aspect of safety where closed circuit television is in place. we need to remember that we should keep all sources, natural and artificial, away from the field of view. We have to make sure that illumination is uniform so that shadows and dark spots are avoided. Instant switch is very important, so for that reason halogen and LED lamps will be preferred. And infrared radiation is mainly emitted by halogen lamps, but also special LED lamps emitting in the infrared can also be found in the market. And I'm saying this because infrared sources are very important for security reasons. So when it comes to closed circuit television systems, halogen lamps and LED lamps will probably be the ones dominating this application. Now there's a few medical issues we need to discuss, but before we discuss them, it's important to make sure that everybody understands that whenever a medical issue is to be discussed, first we discuss it with a doctor, and then we take advantages from light source experts. So having said that, I need to say that a mercury issue is something we need to take care of. The Minamata disaster is unfortunately a very known disaster where the industry poured mercury into a lake. The fish in the lake converted mercury into organic mercury, and then people suffered from the consequences. So we need to avoid lamps containing mercury. Actually, mercury is in the list of the hazardous substances that need to be eliminated according to EU regulations. So high pressure sodium lamps contain mercury, so should be avoided. Some metal halide lamps contain mercury, that should also be avoided, and all fluorescent lamps contain mercury. Now, if you need to use a fluorescent lamp, but you are in a sensitive area, such as a kitchen, there are lamps that have a protective kind of film that contains the mercury in case of breakage. The photograph of Johnny Depp in the film Alice in Wonderland shows the character of the Mad Hatter, and this expression, the Mad Hatter, meaning a crazy person, probably comes from the fact that they used mercury in hat making, and this would probably, unknown to people at the time, would probably cause to serious neurological damages. There are people with photophobia, so in that case light sources and lighting systems that could be controlled, the levels of illumination could be controlled, is what one would be looking for. And in this case, the easiest systems to be deemed or controlled are LED systems and halogen lamps. Then there's the issue of color blindness, and here the answer is quite obvious. LED systems offer the wide variety of colors to choose from. Of course, you can use fluorescent lamps with appropriate phosphors, but to be honest, LEDs coming in different colors is the easiest way to tackle this for colorblind people. Another thing is that we have to be careful of UV exposure. In all cases, we need to shield people from UV radiation with outer bulbs, with doped cords, and with protective covers, depending on the lamp that we are dealing with. We need to check lamps for damage and replace them regularly if we know that UV is emitted. So basically, pretty much all lamps contain a little bit of UV light, except LEDs, because LEDs, like we said, has this narrow and near monochromatic emission. You can find LEDs emitting UV or infrared, but mostly the visible light LEDs avoid these radiations if they're not needed. A few words about eye conditions and the golden age and senior citizens. As a general rule, older people benefit from light sources rich in red emissions, i.e. warm white sources, because as they age there is a reduction in the transmittance of light through the lens of the eye and increased scattering, particularly at short wavelengths such as blue light, causing glare and discomfort. In accordance with practice of wearing sunglasses that cut off most light at wavelengths below 550 nanometers, thus reducing eye lens fluorescence and scatter from the short visible wavelengths and UV radiation. They benefit by enhanced color contrast, so we're looking for high CRI sources and higher illumination levels, but trying to avoid glare, of course. Halogen lamps gives the highest color rendering and emits mainly the red region, so color contrast and light penetration through the lens is optimal. But also another option is warm white fluorescent and LED lamps of high CRI. Now flicker is something that could cause headaches and other problems to photosensitive people, because flicker is caused basically by the fluctuation of the mains voltage. Now one would assume that flicker exists in halogen lamps. It's about a 10% flicker. Flicker exists in fluorescent lamps. The old magnetic ballast fluorescent lamps had a high flicker of 40%. With new electronic ballast, the flicker is down to 15%. Now one would assume that LEDs, they operate with DC currents, so flicker will not be a problem, but this is not the case. With LEDs, you either have a zero flicker because they have the right electronics to eliminate it, or if the controls of the LED are such to operate in near pulsing mode to save energy, then the flicker is quite high. It's an 80-90% flicker. The easiest way to detect whether the light source in front of you has flicker is to put your mobile phone camera into camera mode. Now the frequency, the refresh rate of your screen is different than the frequency of the flicker, so basically what you will see if there is flicker is dark stripes on the image. If you see your light source operating in a clear image on your phone, it means that the flicker is non-existent or very, very small. If the flicker is significant, then the display of your phone will show it in a fashion of these stripes that I'm showing on the images. So fluorescent lamps that employ electronic high frequency gear, and in particularly warm white ones, are of low flicker. LED systems with self-correcting circuits, current feedback circuits, will also have non-existent flicker, and use your mobile phone to detect it. To close this course, I would like again to summarize some of the points made that basically reflect the overall spirit of the proposals made. So many parameters must be taken into account, but once the principles on which the proposals are based on are taken into account, any situation can be evaluated and the right selection of light sources can be made. If one visions a lighting system that could be installed and by appropriate programming accommodate any need or application imagined, then the LED technology seems to be the closest one to realizing such a scenario. And finally, the correct choice of light sources and the appropriate lighting design can make the difference between a comfortable and problematic everyday life, or indeed life and death. The last couple of slides again are dedicated to some of the books I've written related to these light source technologies and the principles of operations, and related to everyday applications and how we match technologies to needs. And basically the slides contain reviews by world experts about those books. They are pretty positive reviews, and I hope that if you need to buy a book to delve more into the subject, then this will convince you that I'm proposing the right books for you. So thank you for attending this short course on light sources, light source technologies, principles of operations, and matching sources with everyday needs and applications.